hobbyist, programmer, and musician. I would like to thank RacketCon for having me present here because this is tangentially related to Racket, but again, there is Racket code. All right, if you know me, you might know me online as Tagbody the Ultimate on Discord, but my name is Asher, and this is what I look like. All right, contemporary music. Here's some, if you haven't heard it. Oh. Can I get it to play to the...
Lord, I don't walk on us. I was not told there would be a quiz.
I'm
Sure, explain to the HDMI.
Yeah, let me try.
What the hell? Say louder.
I just want what? Yeah.
Yeah.
No.
You some. I will miss my son. Imperious, not but imperious.
Right. Okay. I remember.
One has HDMI.
Okay. Let's try
I
that.
don't base
Perfect. Okay. This is some contemporary music. That was by Michael Finnessy. It's from his work called English Country Tunes. This one is by Brian Ferneyhough, and it has the title on it. It's Lemma Icon. All right. Because contemporary classical music is pretty obscure, I just wanted to initiate people who aren't familiar into what it sounds like. But yeah. So why does it sound like that? Now, I love contemporary classical music, but can you guys hear me?
Yeah, there.
Okay. I love contemporary classical music, but I mean, it isn't like, Mozart or whatever. It's
Beethoven.
yeah. It's not what you expect when you hear classical music, but this is the continuation of the Western classical tradition. And it's like that because composers are, instead of concerning themselves entirely with sonic aesthetics, they are interested in exploring texture and form. And form is what interests me because of system in composing music. Traditionally, you would compose music like from the heart, you hear it in your head and then you write it down. But contemporary composers like to start with systems that help guide the compositional process, even if they use, obviously, their ears to, tune it to the final result. Some examples of systematic composers are Arnold Schoenberg, Pierre Boulez, and Conlon Nankero. Here are some examples of their sketches for their works. This is some Boulez, and I'm going to play it.
Yeah. It's a
Okay. This is a sketch by Ferneyhough, which you heard some at the very beginning. An interesting subset of systematic composition is composition assisted by computer, which is sort of necessarily systematic if you're programming your computer to do something. And some examples of composers who do that are Clarence Barlow and Alfred B. Here's some of Clarence Barlow's compositional process. You can see it's pretty involved. This is from a dissertation that he wrote about this one piece, and I'm gonna play some of it for you. If you have a sharp ear, you might have detected some notes that were out of tune. That's intentional. He has you detune the piano. Anyway, one other interesting subset of systematic composition that I like is when you convert something that isn't music into music somehow. And probably the best known person for this, best known composer, is Iannis Xenakis, who's a Greek composer who most of his compositions are high concept pieces where you have like a mathematical function and then it's interpreted as music somehow. this is an example, or that is an example of the formula underlying one of his pieces called Pito Prakta, and it sounds like this. It's a simulation of gas particles in a medium, and I think it captures the sound of gas particles pretty well, because it sounds like what gas particles would sound like if they made noise when they interacted with each other. These are stringed instruments hitting the strings with the bow.
I am out. What time test?
Sorry. Anyway, I came across a piece a while ago called For Clive Barker by a composer named Matthew Lee Knowles, and that piece is an example of the non-music into music subset of systematic composition, where he took a book and turned it into music by converting the words in it and letters individually. That's just an image from it. It is 26 hours long. Yeah. And another composer who goes by Wilhelm online is trying to reverse engineer exactly how it works. And you can see how, I mean, even if you can't read music, you can see how the words are mapped into different things in different contexts. But anyway, I looked at this and I thought, what if I did that with a program instead of, just English text? So my first thought was to take something like some old assembly. This is from Lisp 1.5, the earliest surviving version of the first Lisp implementation. And you can see it's pretty wordy. There's a lot of information on it. Here's a more accessible form than a scan of a printout. But I considered doing this. I considered converting it into music somehow and decided it would be too difficult to make it interesting because there's just too much stuff going on. So instead, what about the Lisp 1.5 language itself rather than the assembler implementation of it? So Lisp 1.5 is a very simple language. It pretty much has only these constructs, and lambda isn't even really a thing. So it has like 7 constructs in it, which is nice because that means fewer different things to have to give a musical interpretation to. And Lisp 1.5 is nice because there's a lot of Lisp 1.5 code available compared to other languages that are this simple. Like early scheme is simpler and would be better, but there's just not that much early scheme code. So most scheme code has syntactic extensions that would be annoying to deal with. Anyway, here's some vintage Lisp 1.5 code straight from a scan of some punch cards. And yeah, this is how they wrote it. This is from the first Lisp compiler. And it's just hideous. Anyway, if you're interested in these old programs, I have some pages about them, like how the compiler works internally. So anyway, okay, back to music. Here is one interpretation of music as a tree. And I saw this a while ago too, and I thought, that's really cool. What if I try to do that when converting code to music? Like, map the tree of expressions onto this tree of chord progressions. I didn't end up doing that because it's too difficult. But let me play this. Anyway, as an aside, there was a guy, someone did make a computer compose music using that sort of structure. This was produced by an algol program that was based on an affix grammar sentence generator, and this won a computer music composition contest in like 1965, and here's the beginning of it. Okay. Anyway, here's some of the code he used to write that, and you can see why I didn't want to do that, because this is also horrible. But anyway, all right, here's another way to convert music to a tree, right? You can just subdivide the rhythms in half at each step. and then you can subdivide them differently too. But basically, every time you step down the rhythm tree, the durations of the notes get shorter. So my idea was to take the Lisp code, and as the Lisp code gets more deeply nested, the rhythms and durations get shorter. So the pipeline for this sort of process is Lisp 1.5 code through the Racket program that converts it to LilyPond, which can then produce a MIDI and a PDF score. The PDF score is really just a vanity feature because I like looking at it, and it's easier to debug than listening to a really long MIDI. But yeah, also I don't have to teach the computer music theory because LilyPond can take care of that for me. So anyway, the data structures for representing music are pretty simple. That's basically it. A note is a collection of pitches and duration, which for annoying music theory reasons is represented by stupid numbers. And then a tuplet is for subdivisions other than into powers of 2. And then a measure is really, in this case, it's just a grouping of notes that has a label because I didn't bother with meter. Anyway, this is the basic procedure for converting Lisp code into music. Most of the pitch content comes from musicalized symbol and musicalized constant, which work on the atoms of the tree. And then the rest of this, and I wrote it using LP2 in a literate style because I like it. So these are just placeholders. These are there in the actual source code. Anyway, the structure of the tree determines the rhythm and stuff, but the atoms determine everything else. They determine the pitch content. And yeah, you can see there's a whole lot of state up top that is threaded through all of this because I wanted to get a lot of variety. Here is, Here is an example of the set cue musicalizer, which does a bunch of stuff. But the idea with set cue was to convert it into a change in volume because of mutation, So every other set cue, it gets louder or quieter. Every set cue gets louder or quieter depending on how many set cues have been seen so far. And then here is the function that converts a symbol into music, into pitches, and it's literally just mapping a function that converts an individual string into pitches and then making it into either a chord or notes depending on how fast the context is to make it playable. Because my goal with this wasn't just to see what it would sound like. I wanted to get actual music out of this for people to play. So what are the results? Well, initially it looked like this, and this is not good because no one can read this. So I tuned it a lot to make some more sane output like this, and I'm gonna play this. This isn't good, but it's better. Anyway, you can hear what it sounds like raw. And again, I love contemporary music, but that is a passable imitation of it, just created from a Lisp compiler's source code. Anyway, at one point I made a mistake in the algorithm, and it produced something that looked like this, and I mean that sucks, but I decided to just roll with it and turn it into, now it's a contemporary piece because it uses weird notation. And it sounds like this. This audio is thanks to Jared over there, who ran it through an organ synthesizer. Let's hope it's not too loud. Oh, baby. Right. It was too loud. Here's another one. This is a function from the Lisp compiler that ended up looking really cool, so I decided to clean it up a bit, and now it's playable and edited to sound a bit more interesting than what this sounded like. Anyway, here's the next Anyway, you might see why I thought code might be interesting for this, because there's little moments of repetition that kind of sound like motifs in music, and yeah, I think it sounds awesome. Anyway, here's another one. This is from the Lisp 1.5 manual. It's a little proof assistant here, and it sounds like this. So again, with the sort of motivic development, you can hear this like D sharp to C sharp thing that gets repeated just because the code is so repetitive with how many times it uses like member and atom and cons and stuff. But anyway, okay, but can it sound good? So you can vary how the characters of a symbol are turned into music or turned into pitches. And one way is to restrict the scale to notes that generally sound good together instead of essentially just any note ever. And so here's what that sounds like. This is a little scheme evaluator I wrote in Lisp 1.5. And there's a particular section of it that sounds decent. And I mean, it's the exact same like structure. It just uses notes that aren't super dissonant. So I don't know how you feel about that. Anyway, here's another interesting fragment from the Lisp evaluator. From the scheme evaluator, this is a test case, which is just the factorial defined using the Y Combinator. And because it's a constant quoted list structure, it is interpreted differently from actual code, and it has a weird wonky rhythm to it. You can see the debugging output where it tells you what the symbols correspond to in the source code, because otherwise it's really hard to, see what's going on. Anyway, I think the results are pretty decent for what I was trying to achieve, which was, make some contemporary music. And Lisp 1.5 is a very tiny language, and there isn't that much code in it. I mean, there is a lot of code in it, but there is more code in other languages. So eventually I might want to try doing this with something like C or Racket, because there's a lot of code in those languages to convert to music. I think as a tool for composition, as like a laboratory for composition, it's really fun to just run this on code and then tweak the parameters and see what results you get, which is how all of those pieces were created, or excerpts were created. and then you can take ideas from whatever the computer spits out, or you can adapt it into a more, complete composition. But yeah, that is about it. Thanks.
All right, questions?
Shit.
Yeah, so I thought this really cool project. You mentioned near the end trying to make it sound pleasant, so to speak, by restricting the scale that the output operates on. Did you try it the other way around, trying to keeping the original note interpreter and trying to write a function in Lisp 1.5 that would make a pleasant noise?
I thought of that. I tried it a bit, but it's really hard. So I didn't get anywhere with it. But it would be a cool kind of code golf to try to write something specifically so that when run through a completely arbitrary process like this, it sounds good. But yeah. It's a cool idea.
Did you run it on itself? And if not, why not?
I didn't because it isn't written in Lisp 1.5, unfortunately. It doesn't support all. If I ran a Racket program through it, it would be completely misinterpreted. I mean, the results might be cool, but it wouldn't reflect the structure of the program in the way that those reflected the structure of their programs. But if I did Racket, then obviously the first thing I would do is run it on itself.
Oh, yes.
Yeah.
One thing this reminds me of, I don't know if you're familiar with a group called Oulipo out of France, and what they looked at a lot was creativity under constraint in sort of summary. And so this reminds me quite a bit of, let me give an example for the group. You write a poem and then you take every third word and you replace it with the corresponding word in the dictionary that's 3 pages across and 10 words down. And then that's your output, right? So how do you be creative under constraints like this? Or you write a book about a disappearance without using the letter E. And so the text of the book is also about the disappearance of this letter. Music and computer-generated music sounds like a nice laboratory for this same kind of exploration. So I wonder if you've thought any about other kinds of constraints on the computer-generated music beyond the structure of the code that would be interesting explorations.
Yeah. Again, I did initially want to do a tonal system where it generates chords that make sense, and then within those chords, those chords guide how the code is converted to music. So when it's I'm going to use some music terms. When it's a dominant chord, it would be using notes that belong to the dominant, to the scale built on the dominant of the key. That would be cool, but again, I didn't. But yeah, you were right. There's a lot of things you can do with this idea.
When you were showing your structs, your definitions of your structs, I noticed the mutable keyword for your note struct. And I was a bit curious on why you would need to mutate a note.
Yeah. So the reason is in stuff like the musicalized symbol. Okay, I actually don't do it here, but it's really annoying to traverse the music structure and then recreate it. So I just made it mutable to make it a lot easier to say get all of the notes and then add something to the first and last one, which is pretty annoying to express when you're traversing a tree that has a bunch of tuplets and stuff. But if you get the notes into a list, it's really easy to just set the field on the first and last one. So it's convenience, basically.
Have you heard of this library called Object Hackna? I think Jared had a question. Go, CLM.
You mentioned that you were using LilyPond for the backend. Were you generating its little DSL or the Guile scheme API for it? And if so, did that influence the design of your data structures?
All right. I'm going to be honest. I did not once consider generating scheme code to make the music. That's a really good idea. No, I generated LilyPond code. But I didn't let that influence anything because it actually isn't that difficult to generate LilyPond. It's difficult to write it, but generating it is easier than writing it. So, yeah. Does that answer your question?
Yeah.
Cool.
Hey, Jared. I was curious if your interpreter interprets, like, do you need every form in the language to have an interpretation, or can it do partial? Can you provide a partial interpretation?
Well, it will just take whatever you throw at it and turn it into music somehow. So if it doesn't recognize syntax, it will still produce something. But Lisp 1.5 is so small, and like the code that exists does not do a lot of syntactic extension, that you can pretty much support the whole language and not a lot of code.
That makes sense. Yeah, as a follow-up, I was just kind of curious, like, have you thought of, like, maybe you provide some rules, like define musicalizer and then make a few rules, and I can, like, implement it, and then I can add musicalizers on top of that?
Yeah. So, like, the state here is a whole bunch of stuff, and this just screams, like, I need to be encapsulated and extensible somehow, because currently to vary the parameters, you have to, like, vary the parameters, which means changing the code. So, yeah, I would want eventually to add support for, like, having you can define like a pattern that when it matches, it runs your musicalizer or something.
That would be really, really cool.
That would be really cool.
Do it happen with? Sure. Yeah.
So when you're evaluating a program and you do beta reduction, you end up substituting a variable for a term. Have you tried playing something before and after beta reduction? And if you haven't, do you think you would be able to hear the substitution?
That's another good idea. I was thinking, like, listening to a program run isn't very interesting, except for maybe lambda calculus, where it's lovely to watch a lambda term expand and reduce. So I think that would be really cool to try, but not for Lisp 1.5, because Lisp 1.5 does not have lambdas in the excuses. It uses dynamic binding, and it's like.
It would also be fun to listen to see what it sounds like under different reduction strategies.
Yes, that is true.
Since you're from Austin, in the UT library, there's Dan Friedman's dissertation written in 1.5, and in his honor, I think it would be wonderful if you turned it into music.
Yes. What is it?
Dan Friedman is Grapple. It's a graph processing language. Dan Friedman is the great-grandfather of this community.
Okay. So the big issue with that is whether or not it's digitized yet, because if it's not, then someone will have to enter it into a computer to run it through the program. So that's the major impediment.
It's on punch cards.
Okay.
All right. I think that's a nice time to wrap this up. Let's thank our speaker one more time.